Hi everyone. Thanks for having me here. So my name is Siddharth. I used to work for Prudential for past 4 years in the AICUE, and now I'm currently on a hiatus, trying to figure out the algorithmic trading on quant industry. So I was excited by the concept of reinforcement learning, and I found that it's not vastly applied in the finance industry, not just in quant, but even in insurance and other verticals. So I thought like, okay, why not? Let's try out RL in finance rather than the plain machine learning. So here I am. So in this particular talk, I'm going to introduce the concepts of the fundamentals of RL. What are the core verticals that operate the RL model, and how can it be applied to the financial world. So let me start. Okay, so this is the outline of this particular talk. So I'm going to introduce the what is RL, the components, the algorithms that are used, and the model-free RL and model-based RL. How trading can be used. So I'm going to focus more on trading as of now, and then I'll talk about the challenges and the future scope. Um, Going ahead, so this is the overview of RL. So RL forms in the niche intersection of a number of verticals such as your reinforcement, the machine learning, reward system, optimal control, and operational research as such. So for us, it's mostly the machine learning part that excites the most, combined with the reward system. This particular image is obtained from David Silver. So David Silver has a very good and rich course on reinforcement learning that you guys might be interested in into this. Let's go into the characteristics of RL. So what is RL? RL is a branch of machine learning which relates with what reward or what reinforcement am I going to get by performing an action. So for each action that it takes, it expects a reinforcement. It might be positive, it might be negative, and it tries to obtain the maximum reward in the positive direction and tries to take the action for each state. And this is quite different from the traditional supervised and unsupervised learning, where you have a label and you regress your model against those labels or the values. But the reinforcement learning tries to pick up the actions that would actually maximize my reward. And a reward, when I speak about it can be very different with each phase. So let's say I'm in a casino and I have 4 to 5 arms to pull out to get the lottery. That is itself, it's a variant of RL, which is called multi-arm bandit. And when it comes to the real world trading, then the money that I get, it's a reward. So this particular concept can be applied to a wide arena of field, but the reward and the policy is the crucial part of how you design it. So these are the core components of RL. So policy. So policy is the agent's behavior function. How does the agent or is going to behave for a transition from particular state S0, say, to state S1. So there are basically two types of policies. One is the deterministic policy and second is stochastic policy. When I say deterministic policy, it is mostly to deal with there is a fixed path by which the agent has to go from each of the states in order to achieve his goal. Let's say from S1 to S2 to S3 and S4. Let's say S5 is my final goal. That would be a deterministic policy. And what is stochastic policy is that there would be a probability assigned to each state. So there is a probability that the agent would go from S2 to either S3 or S4. So there is a probability assigned to each of the states, and that is a stochastic policy. The other component is the value function. Value function is just the cumulative sum of all the rewards that the agent is going to get for each action that he's going to perform. The next one is the model. So basically model predicts what would the environment do next. So it's basically on the observability of the agent across the environment. It tries to see that what state am I going to move into, and what is the reward that I'm going to get by moving into that particular state, and it takes action based on the reward. And speaking of which, reward is anything that the model receives as a reinforcement for each action. So because we are in the financial world, I would say every dollar that you earn in your bank, that's a reward for the model. Moving on. So reinforcement learning traditionally has this simple concept of observation, your environment, action, and reward. So think of it as a brain in which constantly absorbs its surrounding. It takes some action. It learns on its own that okay, some actions I should not be taking right now, or some actions I should be taking it in the later time, and that's how it maps its reward. So there are a lot of variations in RL. I'm not going to cover everything because it's a huge area, but I'm going to focus on model free and actor critic model, which is an intersection of both. So these models, when I say model free, model based, and actor critic, are nothing but everything is focused on 3 to 4 concepts of the Markov decision process. So before I jump into that, I just wanted to introduce the huge hierarchy of algorithms that is available in the reinforcement learning. So OpenAI has drafted this beautiful chart where you could see the big uh, hierarchy of algorithms that is available. So model free, model based are the two big components. And speaking of which, of model free, there are policy optimization and Q-learning, which I'm going to focus more. The second one is the model based RL, which is the most famous Alpha Zero algorithm is actually based on the model based RL. If you're interested more on each of the architecture, feel to go to the link mentioned, and you can learn. The next important piece differentiating the two things is model free and model based. So when I say model free, the model is trying to get some reward based on some trial and error. Let's say let's go to that casino example. I try multiple combination randomly at the start. I learn by mistakes, and I note it down and go on and explore and exploit my iteration. However, model based is more on creating a mental map to work out on the longer value of each action at its current states. So it basically computes its value. What will happen if I go to each state, and it is kind of an unbiased, so it will give equal weightage to each state. It will try out each state and then make a mapping and then take a decision. Whereas model free is just it will start randomly, it will quickly converge to a path that it feels the best, and take its decision thereon. So these are two different ideas. So one simple example is as given in the diagram below. So if you are going through a model free approach, you stop at a junction and decide that okay, today is a Friday evening, I should just go straight and avoid the freeway. So this is by the past experience replay that you have encountered by n number of iterations, and you just take this decision. Whereas in model based, you actually calculate for each street and each road to your destination and say okay, by this approach I get the longer reward, so probably I should avoid the freeway and go straight. It's basically just the difference between the calculation of the values. So these are the two different models that I think everyone would be familiar with the Alpha Zero game, so it was quite famous. So DQN is the deep Q network, for which this is a model free approach, and the other one is Alpha Zero, which is a model based approach. Although technically some of the components is indeed model free, but it does have a mental map of creating the structure. So when it comes to a game, So let's say, uh, for the sake, you have a game with two players. At each step, a model-based model will try to see that what are the n number of combinations that I can take at this particular step. What will be the step that my opponent is taking? How will it impact me? And there on and therefore. So if you could see, there's n number of possibilities that goes on, and sometimes and also the uh, function is such as that it's exponential. So if you have too many of actions, then the competition can go quite high, and even the q value, which is basically the one that goes behind the value, the model. So it becomes complex, and I'll jump into the mathematics in a moment. So this is Bellman equation. Bellman equation is one of the important equation on which the q value works. So if you could see, this is fairly a simple equation. It states that it's a summation of the reward that the agent is receiving for the given state by an action, plus the maximum value it has obtained previously in its older steps. And you can see the gamma function here, which is the discount factor. So it controls the importance of long-term rewards versus the immediate one. So it is as simple as an LSTM forget gate, which uh, determines how much it has to remember and how much it needs to forget. It's something similar to that. So the important characteristic is that we depend on the Markov state assumptions, and the recursive nature of the Bellman equation allows the rewards from future to propagate to the far off past states. So I'll jump into the Markov state assumptions in the next slide. So Markov decision process (MDP) is the like the main function on which most of the RL models are defined. So almost all RL problems can be formalized as MDPs, and there's um, a diagram at the bottom where you can see that for a student from class 1 to class 3 and then passing, all are defined as states. So what it basically says is that for predicting my next state, all the data that I need is just the present, and it doesn't need the past historical data. So that's what the fundamental property. So as you could see, that if I have to move to class 2, the probability is 0.5. But at the same stage, if I spend too much of my time on Facebook, then and I get stuck in that particular loop with high probability, possibly I'm just going to stay there and never going to move to the class 2. And if I going to sleep a lot, I'm going to get stuck there. So that's how the state transition matrix is calculated. So this is a phi tuple for which on which the Markov decision process is designed. The states, all the states in which the agent is going to go to, all the actions that the agent is going to take, the reward, and the probability, the transition probability function, which I just mentioned in the previous chart. And P naught is the start state distribution. So it's just the initial state. Moving on, the Q learning. So Q learning is it falls in the model free approach. So what it does is generally creates a table of, for each action and for each state, what I'm going to earn. So let's say in this particular game, you see that if the robot is going to go to right, it is going to get some points, but if it comes to down, it's going to blow up. So let's say the end is going to get a reward of plus 100, and for each the electric star, it's going to take 10 points, and if it hits the bomb, it's going to have 0 reward or minus 10 reward. So the model will take each step in each directions and try to create a table and store all the values. So by doing this, it tries to know, okay, if I approach one particular path, I'll receive the highest reward. So maybe it is going to go directly to the right and to the bottom and go to the end and say that okay, here's my reward. But alternatively, it can also go and collect all the stars in its path and then go to end, then it has more reward. So this is the way it will reach the end and store the key values. So when it comes to deep Q learning, we obviously have to have theta, which is the parameters that the model is going to learn throughout the model run. So how the cost would be calculated is simple. We just rewrite the old equation of Q value, and we have to sorry, we have to update this particular Bellman equation as a simple update rule. So there is some difficulties in Q learning is because of large set of actions. So let's say you are encountering a problem where the number of states is close to infinite, and you cannot keep calculating the values for all the states and all the actions that the agent can take, and it could be a cumbersome to even to maintain that table. This is where the policy learning comes into play. The policy gradient is much more robust than the Q learning, so it simply evaluates which action should it prefer and doesn't try to evaluate each action. So it is more of trying to get the probability of selecting an action as output. So instead of mapping from theta to Q value and then the policy, it directly sticks from the parameters to the policy. It doesn't calculate the Q value. And how do you optimize the weights? So the optimization in the previous one was using Q values. Because Q value is not calculated here, there is a separate approach here, and we can start with a simple plain vanilla generic update rule, and I'll come on to what's J here, but the theta t plus 1, so we are for the next state we are getting the current state's parameters plus the learning rate and the J. So what's J is the performance measure, which is the most crucial one. So in this particular case, J is nothing but the cumulative sum of for all states what is the key value plus the probability of the action. So the summation of all the Q values for a certain state with the probabilities is called state value function. So as you could see in the next equation, which is the we calculate the gradient, the change in the J theta of t. This is given by this particular equation, GT, and GT is the total accumulated reward from step till T till end of the episode. So what I say by episode, it's much mapped to the epochs in a deep learning. So for each time t, you just calculate what is the total accumulated reward. The derivation of this particular equation is given in the reinforcement learning introduction by Sutton and Bartow. It's a very good book, which actually goes from the fundamentals and into niche mathematical derivation. So this is an example where even policy Q learning doesn't help a lot. So as you could see, this is a slide that is obtained from OpenAI. So this is a cheetah that is trying to run, and if you could see, it is running in an inverted position. So here the policy design was that if the cheetah is going forward, it is going to get a reward, but it was not stated that if it is going to get a reward if it is going straight on its non-inverted position. Hence it keeps running in that particular direction and goes out of space. So designing the policy is more crucial. Hence comes a picture of actor and critic. So what an actor and critic is that so an ideal scenario would be that the agent would learn the policy in a similar way of the gradient policy method, and also understands that the importance of state and action knowledge, which is in the Q learning method. So actor critic basically combines the both, and we get best of both the worlds. So in this particular technique, what we basically do is that for each action we get the q value for each state, we map it back to the policy gradient, and we get the final output. So in this particular way, if you see, I have updated the equation here. So in the place of the j, I have replaced it with the q of st and at, which is the q value in general, which is from the critic. So we combine both these algorithms together, and we find the model working better. Okay, so this is on the fundamentals of RL. Now I'm going to go deep into the applications of RL into finance. So, being in the finance industry for more than 5 years, I have seen that most of us do machine learning such as classifications, forecasting, and regression problems. But I feel that RL could be applied into some of the spaces, and such as portfolio balancing, insurance policy pricing, robo advisors for asset allocation, etc. On a personal note, I specifically like to use RL for stock market trading. So I, being a passive trader, so I use this particular technique now and then to find out its advantages. So basically, you could use the data from either stocks, your assets, your bonds, forex, etc., and try to architect the problem statement into the RL language, such as you have to decide what is the actor going to look into, what is the critic going to look into. So if for an example, I can say that if I want to have an asset that is going to give me a return which is consistently higher than 10% per se, but I need not take any risk that can end up in negative yield. So this particular problem, you can have the critic saying that, okay, I don't really care about the return going above 10%, but I do have the problem that I should not go in the negative area. So it will try to play less risky and will hedge its position accordingly. So this is an example that I wanted to point out. This is the a recent one of Tesla, where it had gone down literally because of it didn't make it to the S&P 500 because the P earnings was not up to was too high. That means the stock was overvalued compared to its peers. So basically, the rising that the bull that the stock has seen is basically based on the investor confidence, and basically the drop at this particular point cannot be really expected because it's more news driven. So uh, for a for a single model such as LSTM, where you can have 3 to 4 classes. Let's say I can predict if it's going to open high, maybe buy, hold, or sell. But let's say I have a number of stocks and I need to maintain a portfolio. I cannot sell too much, I cannot buy too much. I also need to have certain amount of cash in my liquidity. So how do I do that? So for these particular instances, if we have an RL model where you can pass on the data for various information, then the model could try to learn based on the criticism, or I mean the Q value. Let's say if the risk for the particular stock is going high on the Q value, then you have to probably understand, okay, I don't have to be too risky because I have to limit to my benchmark return. So this is a difference between the Microsoft and the Tesla's PE. So even though by momentum of the stock and the way the stock was rising previously, all the technical indicators such as RSI, um, the Bollinger Bands was projecting upwards, but a single sentiment pulled down the entire stock value. So we have to give the RL the entire environment. So what I mean by entire environment is that the model needs to know what is available in its observation. So it needs to know the trading position, cash value, not just the stock trends data, but also the time at which it's going to enter the macroeconomic data, Twitter, etc. So, for another example is just like Musk said that he himself feels that stock was overvalued and it dropped by 10%. So these things the RL model needs to know. So let's say you have a suite of 4 to 5 models. One of the model controls the signals that the tutor is getting in, and the second model controls the technical indicators, and the third model controls the risk. And the RL model, as an ensemble, would try to control these 3 algorithms. It will try to say that okay, because I'm looking for more of profit this time, even though my risk is saying that I don't need to invest more, it will still invest more and try to get better returns. So this is one of the application. And when it comes to the objective function of RL, I have used Sharpe ratio. Sharpe ratio is nothing but how much return are you making adjusted to the risk-free return. So anything above one is a safe. So if you are, even though you are making good return, but if the entire portfolio becomes too risky, you might want to stay away from it. So one such example is, let's say the model made a profit of 21% today, and it then dipped to 10%, then it went to 31%, and then got back to 2% or -%. But if you, even though you sum the entire return, you might be in the positive note, but there's a lot of volatility here, and probably you don't want to be in that particular position for a longer run. If you are looking for a short-term target, then you can of course play. But if you want to have a long run where the objective is to have a consistent return on an annualized base, then probably you'll be sticking into something called Sharpe ratio, and this would be the policy with respect to the reinforcement learning. So this is my personal trading number. So I have a Sharpe ratio of 1.2. But if I compare with my previous models that I have built for the Indian stock market, the returns are very much similar to what LSTM made. But what I also seen that the training time is longer, and at the initial time of the learning time, the model will try to get as much returns as possible at the start, and will very strongly accumulate the funds and try to get the peak of at a higher time. So let me go to the slide here. So if you could see, there are a lot of peaks out here. So let's say at the initial time you say that 10% profit, it's all I want to make. So the moment the model sees that from your initial position you have gone at a peak, as a smaller peak, it will sell off your position. But maybe there is another bull that is waiting for you, and you might have received 15% or 20% return if you had waited for T more trading session. So this comes to exploitation and exploitation trade-off. You also want to control how much are you willing to wait with respect to the trade session, or you want to make immediate profit as soon as possible. Going further, these are, I have few recommendations if you want to try this out. So there's a library called Zipline, which is very good if you want to backtest any of your models, and this is mostly paper-based backtesting. So it is quite useful to learn. You can start as simple as mean aversion algorithm and or simple forecasting, and slowly you can compare the performance of the algorithm as in you improve your models. And this is an excellent repo, the Awesome Quant, which has which is a repository of all the library related to quant for each and every language from R and Python and so on. So I would like you guys to check this out. And the final is the challenges. So what I saw is that RL is quite sensitive. It overfits much faster rate as compared to LSTM, and also because I'm not able to give the whole view, such as the politics, what is happening, maybe any Trump's comments that might impact my model position, or is there any war that is going on. These kind of things, RL doesn't really give much weightage, and that is one particular challenge that I saw. Although I'm still learning and trying out new papers, I have also included the papers that I have tried in the references and want you guys to check it out. And that's it. Let me know if you have any questions.
Yeah, Icewater is asking, is it possible to ensure better mixing of the sample ballots?
Well, so first of all, we don't know how the mixing was, the sampling was done. Of course, better mixing is of course important. This year, we have it's a very different election because there was a reserved time slot for the senior citizens to vote. Maybe this might have introduced some, unintended bias in the sampling. We don't know. Without actually, knowing how they do the mixing, I can't really say much. And I think there's also some physical limits.
Okay. So the second question is, can we suggest improvement to the process? But I guess like what you mentioned just now, if we don't really have a good idea or understanding of the details, probably that one may be a bit of a challenge, right?
Yeah, because if anybody has suggestions, you should take it up with ELD. Yeah, I can't answer on ELD's behalf.
So do you link up your RL model to live trading, and what is your setup if you have done so?
Sure. So I do not have linked my RL model to live trading. So basically, as you know, we just have five tickers: the open, close, high, low, and the volume that is traded, and that gets usually updated at the end of the day. So I have set it up in such a way that I just get SMS triggers once my model senses, and it runs at the end of the day. So I have not directly linked it to the stock market. I just analyze. I get the recommendation from the model, think about it, and then make it read. I'm still working of linking the model to directly the trading platform. So because I'm from India, I have used there are APIs which cost you, such as Zerodha, which is one of the trading platforms where you can obtain an API and you can pass on your signals, let's say buy or hold or sell to them by consuming their API. And there are a lot of also articles that's available there for getting a good trading setup. But as of now, I'm still backtesting my algorithm heavily before I go live.